Okay, continuing with our related rates here, number 4. So we have an oil tank spilling oil that spreads in a circular pattern. Good idea to get a picture here. All right, with radius r, we don't know what it is. And reading this, we have it increases, the radius increases at a rate of 50 feet per minute. So for A, we're trying to find the change in circumference. Okay, so circumference equals 2 pi r. So the change in that, dc dt, equals 2 pi dr dt. And we're looking at a specific time when that snapshot moment, okay, we're looking at the snapshot moment, r is 20. Okay, when r equals 20, dc dt equals 2 times pi times 50 equals 100 feet per minute. So how fast is the circumference changing? It is increasing by 100 feet per minute. All right, let me change this here. How fast is the area? So area is pi r squared. This is part B, or the second part. So dA dt equals 2 pi r dr dt. So when r equals 20, dA dt equals 2 times pi times r times dr dt, which is 50. So this would give us dA dt. How fast is the area changing? And what would that be? 2,000 pi feet squared per minute, or square feet. So the area is increasing at a rate of 2,000 times pi square feet per minute. And then we had the depth here. We change that color. The depth is giving. So we're trying to find the volume, the change in volume. So we have the area of the circle part times the depth, which would be, what is it, 2r squared plus 1. I'm going to multiply this out first. So not dv dt, sorry, that's just volume. Volume equals, so this will be 2 pi r to the 4th plus pi r squared. Now we take the derivative. dv dt equals 8 pi r cubed dr dt plus 2 pi r dr dt. All right, so at that snapshot moment when r equals 20, dv dt equals 8 times pi times 20 cubed times 50 plus 2 pi 20 50. Okay, putting that all together, you can simplify that, and that would be cubic feet per minute. Okay, next example. This is a classic kind of problem. Something's moving away from the wall. Okay, something's moving towards the ground. Here we have a 10-foot ladder. All right, I want to make this a little darker. Here's my ladder. All right, this is X, this is Y. We have a right angle, this is 10. All right, so this is the picture that I'm looking for. So I have, how fast is the ladder sliding down the wall? So for A, we're trying to find dy dt. All right, so we have x squared plus y squared equals 10 squared. We can consider that our position equation. This is our starting point. Taking the derivative, 2x dx dt plus 2y dy dt equals 0. This we can think of as like our velocity equation. Okay, it's the derivative of the position. All right, and there's something else here. The lower end is being pulled away at a rate, so dx dt would be 2. All right, and don't get tricked because it says it's being pulled away. The x is increasing, okay? So now I could divide both sides by 2, so I'll just get x. So when x equals 6, so we get 6 times dx dt, which is 2, plus y. So that we can figure out what y is, all right? And you do this. This is 6, this is 10, so this would be 8 if you use the Pythagorean theorem, or no Pythagorean triples. 8 times dy dt equals 0. So we get 8 dy dt equals negative 12, and dy dt equals negative, what would that be? 12 over 8 divided by 4, 3/2 feet per second. So how fast is the ladder sliding down the wall? It is sliding down at a rate of 3/2 or 1.5 feet per second. All right, so second part. How fast is the angle between the ground and the ladder changing? All right, so we need to figure out some kind of equation. Here is my theta. All right, here's my angle. So I'm looking for here, how fast is the angle changing? So I'm trying to find d theta dt. So I'm going to have to come up with some kind of equation. So I'm going to use x here. So x and 10. Oh, I'm going to get cosine of theta equals x over 10. All right, I can solve for x here. X equals 10 cosine theta. So taking the derivative, dx dt equals negative 10 sine of theta, and it actually ends up being positive 10 sine of theta d theta dt. Wait a minute. All right, no, that actually is negative. My equal sign turned into a negative and I can't see. All right, no problem. So there we go. So now we solve. We're trying to find dx dt. Right? What I do know is at that specific moment, sine of theta this time would be 8 over 10. All right, or 4/5. So then I have dx dt is 2. I'm going to have negative 10 times 4/5 times d theta dt. So 2 equals negative 8 d theta dt, and d theta dt equals negative 1/4, and we're talking radians, it didn't say degrees, radians per second. So the angle is decreasing at a rate of 1/4 radians per second. And then the last part, let me clear some of this up. The last part would be how fast is, oh, it's not the last part, is it? Part C, okay. How fast is the area changing? So area is 1/2 base times height. So dA dt equals product rule here, plus 1/2 y dx dt. All right, how fast is the area changing at that moment? So we already found dy dt, and we have dx dt. So just plug that in. X, I think this is a specific moment when x equals, what's our snapshot moment? When x equals 6. Okay, dy dt 1/2 times y, which is 8, times dx dt, which is 2. So dA dt, simplifying all of that, if you can read it at all, I believe it should be 7/2 feet per second, So the area is increasing at that point. The area is increasing by a rate of 7/2 square feet per second. So I have one more part. I don't know where I'm going to fit it. What's the acceleration of the ladder down the wall? All right, so with this, if this is our position function, okay, this is our velocity. I'm trying to find how fast it's accelerating. So I'm going to divide both sides by 2 just to make it a little easier. So I get x dx dt plus y dy dt equals 0. And so I'm going to go ahead and, since it's changing, dx dt is changing at a specific rate, I can go ahead and plug that in. So I'm going to get x times 2 plus y dy dt equals 0. All right, or dy dt equals negative 2x over y. Now, with this equation, what I can do is take the derivative of that using the quotient rule. All right, so if you want to find the acceleration of the ladder down the wall, take the derivative of this. So you're going to find the second derivative and then plug in all of the values you know when x equals 6. Okay, so you have x, you have y, you have dx dt, you have dy dt. So this is something that I want you to put in your WISC. All right, so I think that's good enough for today. I would say try the next one on your own, but you probably won't do it, so we'll save that for the next video.